Oh, I'm not live yet. All right. Hello, everyone. Hope everyone is doing well. Let me know if there are any issues with the audio. Let me know if you can hear me reasonably well. Hold on, I need to mute this. And apart from that, I'm excited to be streaming today. So today I wanted to talk about magnets, actually. So there's these interesting fractals that you can make with magnets. I guess just to preview the final thing that I made, let me pull it up really quickly. So this is the this is the final object that I made, the culmination of all of my efforts. So what is this exactly? What is this? Hello, Petrus. How are you? Yeah, so this is the final thing that I made, though I actually made a lot of different animations, and I'll be discussing how I did everything, of course. So what is this exactly? So the idea is very simple. You imagine you have a plane, right? You have a plane like so. Actually, I should probably not be drawing in black. Let me not that. Using my trusty paint. You have a plane of some kind, right? And then you have some collection of magnets on the plane, right? Or you can imagine you have some collection of like metal objects on the plane that are magnetic. Maybe there are 3 of them, right? And the idea is pretty simple. Like, let's say you have a really like long pendulum hanging off some point. This is my pendulum, and there's like something magnetic over here. You kind of mark the location above which the pendulum starts. So you mark this location, all right, and then you run it. You let the pendulum go, and you kind of see which magnet it winds up over. And so you specify colors for these magnets. So you can specify this one is red, maybe this one is blue, maybe this one is green. And you let this magnet go, and you see, it'll do some stuff, and eventually it'll wind up over one of them, right? It'll wind up closest to one of these. So, for example, if at the end it winds up over the red magnet, you would color this pixel red, or you could color its path red, and you let it go over a different point. You see where it winds up. You can color the pixels accordingly. It turns out the system is incredibly chaotic. So if you change the magnet's initial position even slightly, that could potentially change what magnet it lands over. Okay, and it's very hard to predict kind of what is going to happen here. A long time ago, I did a video on chaos theory, and in that video, I made some of these animations, and I wanted to explore the idea a little bit further. So I wanted to get efficiently these pictures and animations. I wanted to show I wanted to be able to show kind of what the paths of each of these magnets would look like. And so that's what's going on in this animation over here that I played before. In this animation, what I'm showing is like the paths of all of these magnets. But you can also just think about the images that you would get at the bottom, just the images where you color every pixel, based on what magnet it lands over, red, green, blue, and so on and so forth. And as I mentioned, this system is incredibly chaotic, so it's like very hard to tell what's going to happen. So as like a primer, let's talk about how one might estimate and solve this kind of thing. Well, the point, so one thing you can think about is if you're interested in computing the trajectory of this pendulum, right? If you simplify it a little bit, basically there are 3 kind of forces acting on this. There's like this force that depends on this distance, between each of the magnets and this object, or each of the metallic pieces and this magnet. Each of these will give you a vector, right, which will create a force that comes from, however the distance between a magnet and a metallic object. I believe it's like a 1 over r cubed thing instead of a 1 over r squared thing. And then there's also like friction involved. So, if this thing is moving around, it should be slowing down as it goes. There should be some dissipation, some energy loss within the system. And apart from that, there's also gravity, right? There's something that points this, straight downward. So there's a force pointing straight downward at every point. And you can kind of add up all of these vectors and you'll get basically the differential equation that you need to solve in order to figure out what is going to happen with the trajectory of this pendulum over here. So let's give it a shot. So basically, the differential equation here is just going to be like, let's say x is the position of the magnet. This is a simplified version here. So I'm assuming that the pendulum stick is extremely, extremely long. And so this differential equation is over here is going to be like this. So the acceleration, and I'm assuming all the masses are 1, of course. So this acceleration is going to be the sum of, the forces, so the accelerations due to the magnets, right? The accelerations due to the magnets. Right. And you're going to need to add in the gravity. And then you also need to worry about friction. So you also need to add in friction over here. And so friction depends on a constant, gravity depends on a constant, and this will also depend on a constant. And so the equations here are just going to be like, sum you need to add up over all the magnets. So you add up over all possible magnets. It's going to be like, let's say y is the distance between the position and each of the magnets, right? And you do y over, there'll be some constant here that's like the length of the pendulum over y dot y. 3/2. This is just the equations for how acceleration due to the magnets works. And then you can add in the gravity term, so g x. This will depend on what that is. And then you also need to worry about friction. So friction is going to be like mu. And friction depends on how fast the thing is moving, so you need to throw in a velocity term over here. And this is going to be essentially the differential equation that we are interested in solving. And so you don't really solve this. You kind of approximate a solution of this using various discrete methods. And the method that you want to use in this case is a method called the Beeman integration scheme. So the Beeman integration scheme is really quite lovely for problems of this type. Well, let me move a little bit to the side over here. So the Beeman integration scheme is really quite lovely for problems of this type. Let me just pull up the Beeman integration scheme so you can see it. Okay, so the Beeman algorithm, it's on Wikipedia if you want to take a look. So I basically just used these two equations down here. Let me just zoom in here. These are the only ones you really need. So you approximate the position at the time after the current time using the position at the previous time plus the velocity times dt, which is the change in time, plus 1/6 acceleration at the previous time. And then there's a velocity term as well that you need to approximate because these equations involve velocity as well, because that plays a role in the friction portion of the equation, right? Okay, so you have that. And then how do you approximate acceleration at the next time? The way you approximate acceleration at the next time is just a discretized version of this exact equation. So the acceleration at the time after this time will be just will be exactly what you think it is. You would have to add up over so the approximate acceleration, so like a next or whatever you would want to call it, would be you write this equation down, but instead of so by the way, y is the distance between the position and the magnet, so you would put in whatever the position is, whatever the approximate position right now is, minus the approximate position of the magnets, divided by h squared. H is some constant that you pick that controls like how long the pendulum is, plus y dot y. Y again is the distance between the pendulum rock and the magnet, and then is y dot y, and then you raise it to the 3/2. So the 1/2 comes from distance, the cube comes from the way like magnetic dipoles work, and you add these up, and then minus g times your previous approximated position, minus mu, which is your friction constant, times whatever your approximate velocity was. So just to write it down, actually, I don't even, I mean, yeah, that's just, you write a discrete version of this equation down, and that basically tells you how to update your acceleration. And then when you know how to update your acceleration, you use the equations in the Beeman integration scheme to update the next position and the next velocity. And then using those, you update the next acceleration, then you update position, velocity, then acceleration, then position, then velocity, and the acceleration. And that will allow you to kind of trace a path. So it's not too hard to write these down in Mathematica to see kind of what things will look like. So here's my first attempt at doing this. So I shouldn't reveal the I shouldn't reveal the final result. This is why you have an edit afterwards to make things look nicer. So for 100 by 100 grid of magnets, that's 10,000 magnets. I'm running the simulation for 20 seconds. dt is 0.1, so the time increment is 0.1. The gravitational constant is 0.2. Friction is 0.07. The magnets are positioned at the 3 vertices of an equilateral triangle, and then you have and then you use the Beeman integration scheme to kind of update the positions of the magnets. So if I hit enter over here, the computer will go through the incredibly labor-intensive process of computing the trajectories of all 10,000 magnets and seeing which magnet it winds up closest to. So hopefully that makes sense. So despite my best efforts to get this to run as quickly as humanly possible, in Mathematica, this is still, unfortunately, incredibly slow. So here's the image that you get. So I set it to do random colors. So, but that's still really interesting, I think. I mean, it shows the chaotic nature of the system. So you see this pool of light green points means if the magnet started hanging over at this position, it ends close to this green magnet. Or if the magnet started here close to this pink position, it ends over this pink position. And similarly over here, if the magnet starts close to this dark green position, it ends over this dark green position. But as the magnet gets further and further away, it's interesting, right? Its trajectories become increasingly chaotic. So you can't quite tell for any of these points on the outside where exactly the magnet will land if you let it go, right? So for example, this point winds up landing over this magnet after you run through its entire trajectory. This point winds up running over, getting to the pink magnet if you run through its entire trajectory, right? So basically what the computer is doing, it's doing the Beeman integration scheme using these differential equations, right? And so for each kind of starting position, for each possible starting position, the computer is kind of like approximating the trajectory of the magnet, whatever it's going to go, and then eventually it'll just like stabilize over one of the 3 magnets. And so, for example, if it stabilizes over the red magnet, this point gets colored. Red. I say as I color it orange. This point would get colored red. And so basically, that's what's going on with all 10,000 points over here. So that's really nice, and you get kind of a very beautiful picture. But it does lead me to think, if it were possible to get a higher resolution, maybe I could get an even better picture. So Mathematica is very powerful, but it's not quite good at this type of thing, just like intensive kind of brute force style computations, you know? So it's not the best at this thing. I did do a bunch of different things to get the code to run more quickly in Mathematica. So I tried to do a lot of matrix operations, but even then it wasn't quite incredibly fast. So my next move was to rewrite all of this code in Python and to see kind of how to get the code running more quickly in Python. So you saw how long it took. I mean, we can like time it very quickly. We can time how long it takes for this code to run in Mathematica. So let's see here. Got my system clock. So it's one. Actually, you know what? I can. What am I doing? I can just do this. Absolute timing. Okay, let's just see how long it takes to run over here. I'm guessing it'll take like about 10 seconds to finish running and compute the trajectory of all the different magnets. So let's see over here. My computer's humming. So, oh boy. Yeah, I'm definitely editing this out for the replay. Wow, it seems like it's taking a lot more than 10 seconds. I think, it took 30 seconds to compute the trajectories of all 10,000 magnets, right? I promised 1 million magnets, but this is just 10,000 seconds for now. So you see how slow this is. This is not very fast at all. But it does successfully compute what happens if you start a magnetic pendulum at each of these 10,000 different positions. Okay, so my next step, so I'm closing Mathematica now. Don't maybe save? We'll save it. I'm closing Mathematica now. And so my next master plan was, why don't I rewrite this code in Python? Maybe it'll run faster in Python. Now, this is the code as I've written it in Python. And I will say to you that Python has a number of incredibly lovely little things that you can do to make this sort of code run faster. I mean, Python in general is faster at this specific kind of thing. But so there's something in Python which I've learned about, which I think is really, really amazing. I'm kind of excited to share it with you. So it's called a broadcasting. Okay. So here's how broadcasting works. It's kind of weird, but I've really fallen in love with it. It's like my favorite thing ever right now. So basically, the idea is very simple. It's like a trick you can use to avoid a lot of for loops in your code. So here's the thing. Usually in programming paradigms, whenever you're having to deal with matrices, some poor soul with a numerical analysis PhD has worked on those algorithms very, very carefully. And so if you can get... So like, let's say you have a two-dimensional array that you're dealing with. If you can avoid looping over every entry of that two-dimensional array and just use the array as like a thing and have it interact with other arrays, that will generally run significantly faster. And so there's this thing in Python which is really wild, which is, let's say here's something that you might want to do. So you might have a list of objects. So for example, you might, actually, this is something that we need to do. So like, let's say you have a list of positions, right? So these are all positions. So these would be the positions of the pendulum, right? And let's say you have a list of the magnet positions here. So you also have a list of the magnet positions. Okay. What you need to do is take a look at every position and then look at every magnet position, compute the distance between every position and every magnet position, right? And so that's a lot, right? So you think about how many loops, how many for loops it would take to do that. So if for every position of every pendulum and every magnet position, you have to loop through and figure out all of their distances, That's kind of a brutal nightmare, right? In terms of for loops, you'd have to loop over all the positions and loop over all the magnet positions and take all of their differences. But in Python, there's this beautiful thing called broadcasting. Let me explain it first of all. So let's say you have an array. So let's say you have an array that is n by m. Okay. And let's say you have another array that is n by 1. Okay. Let's say this first array is A, and the second array is B. Okay. If I, in Python, write A plus B, what Python will do automatically is it will treat, so you're adding an n by m with an n by 1 array. Technically, that should not be possible, but Python, so broadcasting is essentially a bit of forgiveness. So if this dimension is a 1, it treats it like an m. So what it does is, if you're adding an n by m array, so you can imagine this is an n by n rows, m columns, and I'm adding it to an n by 1 array, n rows, 1 column, what Python will do is it'll just, in the answer, it'll basically add this entry to each number in the first row. It'll add this entry to each number in the second row, and it'll add this entry to each number in the third row, and so on and so forth, thereby resulting in, again, an n by m matrix. Okay? So essentially what Python is doing is it's treating this 1 as if it's an m. So instead of treating this as an n by 1, it takes m copies of the n by 1. So if this is like if this was like 1, 2, 3, 4, 5, it'll just make m copies of the 1, 2, 3, 4, 5, and just add them up over here. Okay? And so if you tell Python, and this is in NumPy actually, this isn't love the stuff. Are the VODs available somewhere? If not, it'd be great alongside the edited videos. Maybe I'll put both up. I don't know. I still haven't really figured out. Also, hello Tens, how are you? So the problem is if someone stumbles across the channel for like the first time, I really want them to click on the edited video as opposed to like the long VOD. I'm worried that if they saw the VOD first, they might shy away from the content. It's all shared on the channel. You know, maybe what I'll do is make everything unlisted, so you can just watch the VOD if you want to, but that will reduce the risk of someone who hasn't seen the channel before clicking on it. Okay. So in any case, so in Python broadcasting, so if you have an n by m object and then you add it to an n by 1 object, the n by 1 object will be treated as an n by m object. And so the result will be an n by m. And so the way the n by 1 is turned into an n by m is you just get copies of it just copies the 1 into an m. But it works the other way too. So for example, if you were to add an n by m object with a 1 by m object, then what Python will do is it'll turn the 1 into an n. So it would just instead, so let's say this time it's one like this, 1, 2, 3, 4, 5. In adding these, Python will automatically make copies of this. So it goes down this way now, like 1, 2, 3, 4, 5, all the way down. 1, 2, 3, 4, 5, all the way down. And so you're adding an n. So now you're adding an n by m to an n by m, and you're done. It'll turn into an n by m object. How neat is that? So why is this useful to us? So for example, I had a two-dimensional array of magnet position. So you can imagine if it's 100 by 100, So it's 100 by 100. This is, let's say, at time t. At time t, I have a 100 by 100 array of positions of all of the possible pendulums, right? I also, let's say the number of magnets I have at the bottom of the plane is 3. So let's say I have 3 magnets here that I'm trying to do this simulation over. So at time t, I also have, a 3 by 1 array of magnets, right? Now, what if I want to compute the distance between each of these positions and each of these magnets, right? It turns out it's a super easy thing to do in Python. In NumPy, you don't have to loop at all. So let's say this is the positions, and let's say this is the magnets, right? So the positions is 100 by 100. The magnets is, let's say, 3 by 1. I'm going to treat it as a, yeah, sure, 3 by 1, whatever. Okay, so here's what I'm going to do. Also, you should consider multi-streaming on Twitch and other platforms. The algorithm and categories help people get you find your incredible content. Thank you, Tens. I'll consider it. I thought that it was like not allowed, like Twitch frowns upon it or something. I don't really know. I honestly don't know what I'm doing, but any help is appreciated. But thank you. I'll consider it, I guess. Why not? Why not? Okay. So at time t, you have a 100 by 100 array of positions, and you have like a 3 by 1 array of magnets. But watch this. So here's what I'm going to do. I'm going to just add an axis. So I'll make this 1 by 100 by 100. That just amounts to putting an extra bracket outside this matrix, right? And then what I'll do is add a bracket around each entry of this so that this becomes 3 by 1 by 1. Aha! So now if I say to Python, do positions minus magnets, it will treat this one like a 3. It'll treat this bottom one like 100, and this will treat this bottom one like 100. So if I add these axes, so if I put the 1 axis in front of the 100 by 100, and if I put the 2 axes at the end of M, and I just do P minus M, I will get an answer that is a 3 by 100 by 100 matrix that will contain the differences between all of the positions and all of the magnets in one step. Tell me how awesome is that, right? So it's just one line of code can do that for you. Okay. Now let's say, okay. So now I have, so P minus M is like a 3 by 100 by 100 matrix, right? Okay. So now what I can do is I can just slap an absolute value around this. So now it's still a 3 by 100 by 100 matrix, but the 3 by 100 by 100 matrix now has the actual distances between each of the positions and each of the magnets. So I just took the absolute values over here. Okay, wonderful. Okay, so now I can just, again, this is another neat thing you can do in Python, in NumPy specifically. So if I just say to this, okay, what if I was interested in the closest magnet to each of these? Then all you need to do is like a quick argmin of this, and then specify that you want to do this along axis 0. So what that'll do is that'll terminate this. It'll just replace this first axis with the smallest entry along that axis, and then you'll result with a 100 by 100 matrix. And guess what? That 100 by 100 matrix now contains the magnet index that each of the initial positions was closest to, and you do that with one line of code. How amazing is that? So I love this idea of broadcasting. That's honestly it's like the coolest thing I've learned about recently. And like, it's so good. So, I mean, I wrote out the magnet code in Python. It's honestly just a couple lines, right? And let's see it in action. So let's do, so this is the same simulation, 5 magnets. Let me run it. Okay, so, and then, okay, 5 magnets, 10 seconds. So 5 magnets, well, I'm sorry. 5 pieces of metal at the bottom, and what's 300 times 300? I don't know, like 90,000 or something? Yeah, 90,000. So 90,000 positions are being computed and simulated, right? And that's really cool. So 90 1,000 positions are being simulated for 10 seconds, and then you see, so you get a color based on what magnet it winds up closest to. And I mean, it's very fast, right? So this broadcasting business makes it lightning fast to write code. So if you take anything away from this video, it would definitely be broadcasting, which is, I think, far more useful than it initially appears. Let me run the same simulation, but for like, say 50 seconds. Let's do it. Just kind of see how chaotic, see kind of how chaotic it becomes. So this will take a little bit longer. It should take 5 times as long at least as the last one. And so now, see, now it gets a lot messier, but you can still see there's some interesting patterns over here. Okay. So this is the end to part 2 of this story, because I wanted to make the code faster still, okay? I wanted to make the code faster still. The issue is, with this code, it's running in Python, and this is as, I mean, I'm sure some like Python genius could get it to work even faster in Python, but I wanted it to work faster still. In particular, I wanted to know how, like this, right? How is it exactly that this is what it looks like at 10 seconds, right? Turns into this. So this is what it looks like at 50 seconds. So that's what I was really interested in. I wanted to see how the closest magnet diagram changed over the course of the next 40 seconds. And Python is not fast enough to give me those frames in real time. Okay, enter my next master plan. Okay, my next master plan was to use a shader. So I've never used a shader before. So I was interested in using this tool called GLSL. So this is a shading language. What makes this so powerful? So what makes this really powerful is you can actually send instructions directly to your graphics card, almost. So for each pixel, you can send in parallel an instruction to your graphics card and say to it, okay, I want you to follow these instructions in order to figure out how I would like you to color each pixel. Okay, so this is going to be insanely faster than even doing it in Python, because Python was doing the computations on the CPU, and I wanted to do the computations on the GPU. Unfortunately, GLSL takes a long time to set up. It's very complicated, but there's this online tool that I highly recommend. It's called ShaderToy. I'm going to pull up my ShaderToy right now. So ShaderToy, they basically take care of all of the boilerplate code for you, all of the boilerplate OpenGL kind of code for you. So you can just program in the shader. And so that was really, really useful to me. And so this is what I came up with in ShaderToy. This is my first time programming in GLSL. Okay, and I'm very excited to share this with you. Okay, so I hope you guys are ready. Okay, so what is this right now? So there are 3 magnets, and the color is based on what magnet the pendulum is closest to. So at time 0, all the pendulums that start kind of in this area should be closest to this magnet, right? And all the pendulums that start in this area should be close to this magnet. And all the pendulums that start down here should be closest to this magnet, right? But if I let time progress, all the pendulums start moving around and the situation gets more and more chaotic. And now I want to be able to answer the question of kind of how does the simulation progress from being these like clean lines into something more messy? And GLSL was indeed fast enough to be able to answer that question. So let's watch. All right. And okay, it's going. Come on. Oh, that's so beautiful. Tell me you don't like that. I also darkened the pixel based on the length of the path, and that gives it a kind of depth, right? It makes the drawing look more dynamic and interesting. So that's that's what that looks like. Okay, so this is what it looks like 60 seconds worth of frames in, and you can kind of see just how beautiful this is, right? By the way, for this one as opposed to this one, I turned the friction up slightly. So I turned the friction in the I turned the friction in the pendulum up by a little bit just so you would get a prettier picture. And I do think that that is just beautiful. I'm just going to play it one more time. And then I might try to up the number of magnets as well, just so that, just so it can look more interesting. So let me know if there are any questions about any of this stuff. By the way, this is a nightmare to program in for your first time because there's no console. You can't debug. You can't print anything. So I sitting there for hours trying to figure out like all the little ways in which I'm like messing up my my code. But it wound up working out in the end. One thing that I really wanted to implement was like a drag and drop feature. So like you could drag the magnets and move them around. But I ran out of time. I wasn't able to do that. I mean, one thing we can try to do is add more magnets. It'll probably break the code, but I mean, why not? We can give it a shot. So I do believe this code is set up for arbitrary magnets in arbitrary positions. So let's try it and see what happens. Let's try 4 magnets. 4 magnets in, let's try in the positions. You have to be so much more careful writing code here than you can in like Mathematica or Python, because if you add like a float to an int, it's like, I hate you, I'm gonna explode now. You know, it does not like doing stuff like that. But let's see here. So you need to be very careful about like typing and casting and like all those other shenanigans that you do not need to worry about when you write code in Python or Mathematica. I guess you do need to worry about it in math. Anyways, I set up 4 magnets. Fingers crossed. Let's see what happens. Uh-oh. Okay, that didn't work. Okay, I honestly don't know what this is or what this means. Let me go back here. So there's a magnet at, I put 2 magnets down at -2. So it should be here. Sorry, I overloaded my magnets. Let's go back, compile. Okay, that actually worked. Let's try it. See how the 4 magnet simulation goes. Ooh, that's very pretty. And once again, the darkness in the pixels is coming from path length. So the longer the path of the pendulum is, the darker the pixels get. Also, I just realized that I can like full screen this. Hopefully it doesn't break the stream. But there you go. So this is what it looks like. This is the chaos of a million magnets, a million magnetic pendulums being swung around. Anyways, I'm really proud of this. I'm proud that you can send these instructions directly to the graphics card and, simulate all 1 million of them in real time in order to get these animations. So that's really cool. Maybe I'll do one more. Let me know if anyone watching has a suggestion about how to position these magnets. If you're curious about anything. So right now these magnets are positioned at 2 0, -2, 0, 0, 2, and 0, -2. But we could try, we could try any number of combinations. So I don't know. We could do like okay, I'm gonna you really ought not to program live, but I'm gonna try it anyway. I don't know if this is gonna work. I'm like not good enough with this type of code, but we can do for int I equals 0, I less than magnets dot. How about not symmetrical? Yeah, sure. If you have any suggestions about where to put them, I'm happy to put them there. Actually, I like trying not symmetrical. Let me go back here. How about just like 4 random points? So let's do like 2.1, I don't know, -2.1, I don't know, 3.6. This is probably not going to be random because I'm just like typing it in, but -1.20, and then 3.1, 3.1. Okay. How does it feel? Hopefully that feels random enough. So I'm going to pause this and go back, hit play. So it starts out as a Voronoi. It'll always start out as a Voronoi diagram. Oh, let me full screen. Yeah, that's pretty cool, Petros. That's very nice. Ooh, I love when the when the darkness comes in from the path links. That looks really beautiful. Oh, by the way, I'll put this up, actually. You can go to Shader Toy. I'll make it public. I'll include a link in the description when I put out the edit, and you can just play with it yourself on Shader Toy. Just be warned, the code is terrible. Like, all my code is atrocious, but that's very nice, I think. Yeah, the... All right. I can do one more if you like. But then there's also something else I'd like to show, because I then went to Blender as well to do some more renders, and that's how I produced the initial video that I came up with. So we can try like 6 magnets. I don't know. Let's put 1 at the origin. Yeah, I really wanted to have like a drag and drop thing where you like put, where you can just click on a point on the screen and then put a magnet down, but it's okay. We can just type them in. I don't have any magnets in the third quadrant, so how about, all right, let's see what happens. Oh, jump the gun. All right. If you guys are ready. That's so pretty. Wow. Would you look at that? Well, there you go. Okay. Again, if anyone has any idea about positions, I mean, I'm more than happy to type them in. Also, like I said, I'm making this code public, so you can go to. I'll include a link to this shader toy. You can like type in whatever positions you want. I'm just having a great time. Okay. I don't know. Should I do one more, or should I like move on to something else? I should probably move on to something else. Pause this. Okay. So yeah, I know. I'm happy you like it. Again, if anyone has any ideas for positioning these, we can do that. Okay, so the next thing I wanted to do was I actually wanted to see the trajectories. So I wanted to actually see the paths that these magnets are moving around in order to get to their final position. And so I really wanted to make something like really pretty. I don't know if it came out very pretty. I'm not sure how good I am at like Blender yet, but this is the animation that I played at the start. So this is 900 magnets, and you can see all of the trajectories. Will I keep the video up? I mean, I'll definitely edit it down. So how about making a repulsive magnet? So it's a great idea. The reason it wouldn't work here is because the way I'm coloring each of these points, so the color that each of these points gets is dependent on what magnet it ends closest to, right? But if, you know what? I take that back, Kay. I think that's not the worst idea. I don't feel comfortable or talented enough to edit it on the fly, because right now the equations for all magnets are the same. I'd have to go into the bowels of the code. But, you know, that's not a bad idea. Like I said, I'll make this public if you want to. So there's a for loop in here where I add the accelerations for all of the magnets. It's right here. Here, I'll throw a comment if it helps you edit the code later. Let's see. Compute approximate next acceleration for all points. Okay, so this is the for loop where I do it. You'd have to muck around in here in order to change what's going on. Okay. That aside, I did want to share what I did in Blender. So I don't mind that idea, actually. I kind of like it, but I'm probably not going to do it. Sorry. I can't edit things on the fly. I know I'm going to break everything. In any case, oh yeah, so this is the last thing I basically wanted to show, and this almost broke my computer into a million pieces. But so you start out with 900 magnets, and you just show each of their trajectories as you go on and on. So the good news here is actually you can write Blender code in Python. So wait, you can write, sorry, you can write Python code in Blender. So that's what I did over here. So here, let me open the Blender file. I'll show you how like brutal this was on my computer. So this is my little Blender environment. I have animations and shadings and like various colors. So yeah, this is what it looks like here. This is what it looks like on frame 0. And in any case, I guess Blender has a scripting tab you can go in. And so I copied basically all of the code that I used, that I wrote in Jupyter Python, and I just copied it. I just copy pasted it here, and then I just used that code to create segments, and then I grew these these metallic or I guess like plastic looking tentacles along those segments. So I basically got up to the limit of what my computer can handle, and it turned out 900 trajectories with my skill set was about the limit. It's interesting though. You can actually just see the trajectories. Okay, hold on. I think what I'm gonna do is I'm gonna make a copy of this. Just so I can mess around with it on stream, because I liked the way I left it. I don't want to destroy it. Let me see. Paste. Okay. Photoshop. What am I doing? Sorry. This is just like my thumbnails. Where'd it go? I don't really know why Photoshop opened there. But I just wanted to show you like the magnet trajectories. So I'm gonna go in here, and for each of these, gonna like turn off the this and this. Did that not work? Okay, it's chugging. It's like, it's trying. Hold on. Okay, I need to go in and do it manually. Okay, so I did it for this one. I did it for this one. I did not do it for this one. So I'm like getting rid of the objects that it's mapping along the curves so that you can see the actual curves. Okay, there it is. Now you can see all of the trajectories of all of the magnets, which is really nice, actually. It's pretty cool. And I put these like light bulbs on top so it would look like a Christmas tree or whatever. So honestly, I've just started to use Blender. The first ever thing I made in Blender was the last video that I made. And honestly, it's amazing. It's such a good program. I'm not very good at it, but like, I can't believe all the stuff you can do in it. Like, it's unbelievable how much you can get away with. I try to do as much as I can, like by scripting, but I know that's not the best way to interact with Blender. I guess like one thing I can show you is if we're like, hold on, I'm just gonna erase all of this. I'm in the copy. Yeah, I'm in the copy. I don't want to. Okay. I'm just going to run the script, and I'll show you what the trajectories look like for more magnets. So, for example, let's do 2,500 magnets. Okay, or not. Or it's just like, no, I don't want it. I hate you. Okay, so yeah, let's do 2,500 magnets. And let's do like... kind of curious what's going to happen. This could be the end of it for my computer. If the stream ends, you'll know why. Yeah, typical mathematician Christmas tree. Yeah, thank you. Let's see. Okay. So now there are 10 final positions and 2,500 magnets. Let's go. And the stream could end right here if my computer crashes. All right. I don't know why it's so much fun being so like brutal to my poor graphics card and processor. Okay, I think it's... Ooh, no, it did it. Okay. Cool. So, as you can see, these are... So, for example, here, let me show you. So, for example, these are all the trajectories that end at one magnet. You see that? In fact, I might join these. There you go. So these are all the trajectories that end at one of the magnets. And, there's another collection of trajectories, of course, that end on the other, like the next set of magnets. And so we have 10 separate magnets over here, which is nice. Okay, I think that's about it out of me. I've done all I can say or do. I don't want to waste your guys' time. Anyways, that was a lot of work, but also a lot of fun. I hope you guys enjoyed it. I'll be editing this down and posting it. So To be honest, I'll probably cut out some of the like math stuff. I'm not sure how interested anyone is in that, but I'll probably leave in the stuff about broadcasting in Python just because I love it so much. Also, I forgot to say hi to you, Hitoshi. Hello. I hope you're doing well. I am going to probably head out now. So just so you know, I'm going to try and do only streams on Wednesdays from now on. I can't. So I still work full time. So I don't have time to do 2 videos and 2 edits. But people really seem to like the edits. So I figured I would do 1 video and 1 edit every week. So I stream from now on every Wednesday, and I'll edit it down within the next like couple days, turn it into like a 10 to 15 minute video, just so people coming by later can enjoy it. And then I'll unlist the VOD, but you know it'll still be up in case anyone wants to watch. Regardless, thank you all so much for coming by. You're all the best. You're all amazing. I love you all. And I don't know what else to say. So, peace.